Hi there, folks. Today we're looking at bisectors inside of triangles. So within a triangle, we're going to look at certain bisectors, like segment bisectors, perpendicular bisectors, angle bisectors, that kind of thing. And before we get into that, we're going to kind of see what happens when we do that. And then we're going to look at the properties of those things. The first thing we need to talk about is this word concurrent, all right? And it's not super important that you remember these definitions. It's just kind of a prelude to what we're about to see. But concurrent is when three or more lines intersect, and that's at a single point, okay? So intersect at one point. It's kind of important. Apparently I don't have it on there. Okay, but it's when they all kind of come together at one single point. And we call that point the point of concurrency. All right, so the point of the concurrency is the point at which three or more lines intersect. And again, concurrent is not going to come up a lot, all right? It's going to be used in some of the definitions that we're going to get to today. So as long as you understand, hey, when things come together at a single point, more than, so three or more lines come together at a single point, we're talking about these things are concurrent. So when you see that word come up later, it's just talking, hey, the point where all three of these lines come together, all right? So the first one we're going to look at is the circumcenter of a triangle. The circumcenter of a triangle is the point of intersection for the perpendicular bisectors of the triangle. And right away, when you look at the picture down here, you can see that they're concurrent, all right, those three lines, the three perpendicular bisectors. And so they come together at this single point. That point is called the circumcenter, okay? And there's some special properties here. So notice what I've drawn here is just the perpendicular bisector of each side. When I draw the perpendicular bisector of each side, so we can see the perpendicular bisector of this side is this guy right here. The perpendicular bisector of this side is this guy right here. And the perpendicular bisector of this third side is this one that's going up and down, okay? Those three perpendicular bisectors all come together at one single point, and it's this guy right here. That's the circumcenter, okay? It's right there in kind of the middle of this triangle. And in the middle of the triangle, in the sense that, and here's what's special about the circumcenter, okay? The perpendicular bisectors of the sides of a triangle are concurrent at a point. There's a little typo there. At a point equidistant from the vertices. So when I say it's at the center of the triangle, it literally is at the center of the triangle compared to the vertices, compared to the exterior points. So these guys right here, when you look at these guys, these 3 points that make up the triangle, that circumcenter, that point, is the same distance away from all three of those. Okay, that's what's special about the circumcenter, is that it's the same distance away from all of those pieces. Okay? And so then we also have this thing called circumscribed. That's when a circle connects all the vertices of a polygon. In other words, if I were to scroll back up here for a second, if I were to draw a circle that has a center right here at the circumcenter, if I drew a circle here, it would connect all of those points, okay? That's a circumscribed circle, all right? It's a circle that goes around the outside of the shape, all right? So it hits all of the vertices, all right, and what's special about that circle is its center is right here. Its center is this point where the perpendicular bisectors come together, okay? So again, the perpendicular bisectors come together at a point, the circumcenter. That point is the same distance away from all the vertices, okay? And one of the things that allows us to do is we could create a circle around this shape by connecting the vertices by using that point, the circumcenter, as the center of that circle, okay? And if you want to make a note to self here and say, hey, the center of this circle is the circumcenter. Okay, and I kind of drew a sketch of that up here real quickly. Okay. For example, if I look at something like this, it says the coordinates for a triangle ABC. I've got A at -4, 4. I'm going to just plot these. So let's see. I've got B at -6, -2. I've got C at 2, 2. And so I have this triangle ABC. And I could draw the triangle using some lines here. All right. And it said find the circumcenter. So really to find the circumcenter, I have to draw the perpendicular bisectors, okay? And so that takes a couple things. First of all, I have to find the center of these. So I have to find the midpoint of each of these guys. So remember, to find the midpoint, I just count halfway. So from A to B, let's see, or for B to A, I would go up 1, 2, 3, 4, 5, 6, and over 2. So I'm going to go up 3 over 1. There's the center, all right, of that guy. And then keeping along those same lines, because I had to go up 3 over 2, as I kind of think about the slope of this line, all right, is up 6 over 2, so it's up 3 over 1. So the slope of that line, again, the slope of AB is 3 over 1, which means the perpendicular line would be negative 1 over 3. Okay, so from the midpoint, I just use a slope of negative 1/3. That's down 1 over 3, down 1 over 3, or up 1 back 3, and I can draw the perpendicular line. Okay, and now I just have to do that. I have to duplicate that process with each of these other sides. So if I look at something like BC, that's over 6, 7, 8, and up 1, 2, 3, 4. So I'm going to go over 4, up 2. To get to the center of this guy. And you can see I didn't draw my line very well over here apparently for BC. Okay, there's a better representation of the line. The center of that line is right here. Okay, and I can even see the slope of that line. It's over 2 up 1 over 2 up 1, or up 1 over 2, up 1 over 2, up 1 over 2. So it's got a slope of 1/2. So once again, if I just kind of take that off to the side and say, hey, that line has a slope of 1/2, which means the perpendicular line has to have a slope of negative 2. So right here, from this center point, I would go down 2 over 1, down 2 over 1, down 2 over 1, and I'm just creating the perpendicular lines that I need for each of these sides. Okay? And so, again, here's what I'm creating. I did a perpendicular line here. I did a perpendicular line here. And now I just have to do it with the third side. If I do it with the third side, once again, counting halfway to get from A to C is down 2, and then over 1, 2, 3, 4, 5, 6. So I'm going to go down 1 over 3. That's right here. So that has a slope of negative 1/3. So once again, if I kind of come back over here and say, hey, that first guy has a slope of negative 1/3, my line is going to have a slope of positive 3. So from this center point, up 3 over 1, up 3 over 1, down 3 back 1. And so I can draw the perpendicular bisector of that line. Okay? And so once again, I've just created a perpendicular line. Can you see where all three of those points come together? That's the circumcenter. That's what I've created here. And so if I label this off to the side, that's the ordered pair, negative 2, 0. Okay? And really, when you think about it, I went through and I drew all of the perpendicular bisectors here. But really, would I have to draw all of them? Okay? If I know that all three of those lines are going to intersect at one point, as soon as I see two of the lines intersecting, I know the third line's going to end up there. Okay? So you really only ever need to do two of these to find the circumcenter. Okay? Keep that in mind. The third one's automatically going to intersect at the same point. Now, is there benefit in drawing the third one? Yeah, it instantly checks the work that we've done so far. Okay? And so then the next question here is how would you circumscribe a circle about the figure above? Well, if we understand what circumscribing a circle means, it means that I have to draw a circle that touches all the vertices, okay? Which means that I have to draw a circle whose center is at negative 2, 0, okay? So we would draw a circle. We'd have to draw a circle with center negative 2, 0. And we would have to have a radius of that circle that matches the distance to any one of the vertices, okay? So the radius on this guy would have to equal, well, I could actually find the radius if I wanted to. So from here, to get from one of these vertices, say B, to the circumcenter, it's up 2 over 4. Again, you could do it like your Pythagorean theorem, up 2 over 4. A squared plus B squared equals C squared. So let's see, 4 plus 16, that's 20. So I'm going to do the square root of 20 here, which is 2 root 5. Okay? That's how long the radius would have to be. And you could plug that into a calculator and find a decimal approximation. But that would create a circle, all right? It would create a circle that went through, let me get a different color here. Let's go red. would create a circle that has a center here, and then this essentially would be my radius, okay? This would be my radius. And so if I kept that radius the entire way around this circle, kind of look like this, okay? That's how it would circumscribe the circle. It comes down to using the circumcenter as the center, all right, and then using the distance to one of the vertices as the radius, because all of those distances are the same. This distance right here is the same as this distance right here, is the same as this distance right here, okay? That's what's special about this point. It's the same distance to all the vertices, okay? If I look at this guy, it says find the value of x. So right away, if I'm looking at this thing, if I understand that these are the perpendicular bisectors, and I missed some labels here, let's assume that these guys are equal, and let's assume that these guys are equal. I should have had that as part of my picture. So let's say that that was part of my figure here. I can now tell that those are perpendicular bisectors, okay? And I can tell they're perpendicular bisectors because these pieces are equal, meaning that that line goes through the midpoint. These pieces are equal, meaning that that line goes through the midpoint, all right? And they're perpendicular based on the fact that they're right angles, okay? So if those are perpendicular bisectors, it means that this guy right here must be my circumcenter, okay? That point is my circumcenter, which means the distance to each vertice is the same. So the distance right here on this purple line should be the same as the distance on this other purple line. These pieces should be congruent because the circumcenter is the same distance away from all the vertices, which means, quite simply, in this example, the 2x minus 5 has to equal the 10 minus x, okay? And so I would add the x over to the other side. I would add the 5 over to the other side. I would divide, and that's it, okay? So again, when we draw the perpendicular bisectors inside of a triangle, we get this special point that's equidistant from all the vertices, okay? Let's talk about the incenter. The incenter of a triangle is the point of intersection of the angle bisectors of the triangle. So we did the perpendicular bisectors inside the triangle. Now we're doing the angle bisectors inside the triangle, all right? And once again, you'll notice they come together at a single point, all right? And that point has some special properties, all right? The incenter, all right, when we draw all the angle bisectors, it comes together a point that's equidistant from the sides of the triangle, okay? So the circumcenter was equidistant from the vertices of the triangle. The incenter is equidistant to the sides of the triangle. So right here is the incenter. I see it. It's this point right here. The defining characteristic of that is that it's the same distance away from each side. So in other words, this distance right here, and remember, when you measure distance, you have to measure at a right angle. This distance right here and this distance right here are all equal. And you can see they're about the same in terms of my drawing. But all of these pieces are congruent. This guy, and this guy. That's what the incenter does, okay? So the circumcenter gives us a point that's the same distance from all the vertices. The incenter gives us a point that's the same distance from all the sides, okay? That's what's special about this thing, and that's what this theorem down here is saying. All right. Going along with that, we have something called an inscribed circle. That's when we put the circle inside the shape. So circumscribed was the circle is outside the shape. It's connecting all the vertices. Inscribed, the circle is inside the shape, just touching all the sides. And that's what tangent to all the sides means. Okay. It just touches all the sides. In other words, when I look at something like this guy, the inscribed circle would look kind of something like this. I'm freehanding a circle here. It wasn't too bad. I could have done better, I think. Okay? But it kind of just touches each of these sides, just very gently, just touches at a single point where this guy is the center. That's an inscribed circle. And the center of that circle is the incenter, all right? Because we want the radius to be that distance to the side. All right, so it's a very similar concept, but instead of talking about the vertices around the triangle, I'm talking about being the same distance as to the sides of the triangle. And that idea of circumscribed versus inscribed, very similar, okay? For example, if I look at this guy, it says find the value of x, all right? And the importance with those perpendicular pieces are showing that we're measuring the distance. So right here, these are two angle bisectors, okay? So this guy right here is an angle bisector. This guy right here is an angle bisector, which means the point where they come together, even though I don't have the third one, the third angle bisector will come together at the same point. All right, I don't need the third one to know that this is the incenter right here. So this guy right here, this is the incenter right here, which means that point is the same distance from each side. And that's where these perpendicular lines come into play. When I measure distance, I have to measure directly to the thing. I have to measure at a perpendicular kind of line. So this guy is congruent to this guy. That's what the incenter does. It's the same distance from each side, meaning that the 4x plus 3 has to equal the x plus 15. And so once again, I subtract the x from each side. I'm going to subtract the 3 from each side. I'm going to divide, and I get x equals 4. Okay? But again, it's about understanding. Hey, what do each of these points represent? The circumcenter is the same distance from all the vertices. Okay? The incenter is the same distance from all the sides, and we have to measure to the side at a perpendicular line. And then the next question says, what would the radius of an inscribed circle be? So if I wanted to draw an inscribed circle, again, I have to think about how I would do that. The center of it would be the incenter, and it would just touch each of these sides. That is terribly drawn. I was going to try to draw a really nice freehand circle. It would look like this. And hopefully right away you realize that the radius is whatever that distance to the side is. And keep in mind, I already solved for x, so I know what that radius is. I know what that distance is. I just have to plug that x value in. If I plug that 4 in to this guy right here, that gives me a 19. Likewise, if I plug the 4 in here, that gives me a 19. As it should, those should be the same. That's the radius of this circle, okay? It's that direct distance from that incenter to the side, okay? So in this one, the radius would be 19, okay? But it's about understanding and pulling these concepts together. If you know what the incenter is, you know it's the same distance from all the sides, and that directly relates to that idea of inscribed circles, okay?